In this video, I'm going to look at what's called a modified Atwood machine, and I'm going to show you the system and object method derivations for the acceleration. So when we have a modified Atwood machine, this just means that one of the objects is sitting on a table or a horizontal surface, and the other object is hanging freely. So same as before, we are going to be deriving the acceleration of our system. And when we do the object method, we have to do our free body diagrams for each of our objects. So I'm going to have, for mass 1, the normal force is going to be up, the weight force down, and in this case, there is no friction, so we're doing this without friction, and then tension is going to point along the string. So this is going to accelerate in the direction of tension. For M2, we have M2G down, and then we have tension up. Now, just as before with the full Atwood machine, these two tensions are going to be the same. So this is going to accelerate in the direction of M2G. And just as before, we have to align our accelerations to do this problem. So I'm going to take this free body diagram and I'm going to turn it so that the accelerations are going to be in the same direction. So acceleration is going to be to the right. So to the right is going to be positive, to the left is going to be negative. So in order to find my acceleration, I need to write my two net force equations. So my net force equation for M1 is just going to be tension is equal to M1A. My net force equation for M2 is going to be M2G in the positive direction minus tension is equal to M2A. Now again, I have two unknowns, but my accelerations again are going to be the same. My tensions are the same, just opposite direction. So two unknowns, two equations. I can either use the substitution or systems of equations method, and I can just add my equations together. And then my tensions are going to cancel, and I can factor out acceleration, and I'm going to get M2G. Now to find acceleration, I divide both sides by M1 plus M2. These cancel, and there is the equation using the object method for the acceleration of a modified Atwood machine without friction. But I can do the exact same thing with the system method. So instead of treating these two as objects, again, I treat them as a system. So I circle the whole thing, and I have to line them up, straighten it out. So here's my M1, and here's M2. But in this case, the only external force is going to be M2G. M1, M1 still has its M1G. That is an external force. The normal force is still an external force, but they are not in the direction of acceleration, so they are not going to be included in my equation. So to calculate my acceleration, I'm going to do the total of all the forces trying to make the system speed up. That's M2G. And then I'm going to subtract the total of all the forces trying to make the system slow down, which in this case there aren't any. And then I'm going to divide by the total mass of the system. And there's my acceleration. So I can get the same equation faster using the system method. Now, same thing as we did before, if I did have friction here, then I would have an extra force of friction here, which using the fun equation means that my friction would equal the coefficient times M1G. And so all that would do in this problem is change this to subtract that force that's trying to slow it down. And that's how you can easily modify these equations using the system method.